the beginning of the 1930s, researchers at ICI, Britain's leading chemical producer, wondered what would happen if they compressed gases to 1,500 times atmospheric pressure. It was risky business, because equivalent pressures had only been generated in naval gun barrels. Among the many gases they squeezed was ethylene, and the result was a curious, white, waxy substance. While the product did not look terribly promising, someone actually thought the stuff might be useful. Indeed it was. As a weather-resistant insulation for wiring, it made airborne radar possible and contributed to Britain's finest hour. And that waxy stuff, by the way, was polyethylene. After the Second World War, the prognosis for polyethylene was bleak. Plastic flour seemed like a good bet. The one refinery alone could have supplied world demand for that one item. Today, however, refineries all over the world churn out millions of tons of polyethylene each year. Of all types of plastic, polyethylene is produced in the greatest quantities. And for good reason. As film, it is used extensively in the packaging industry. Molded, it can be fashioned into containers of any description. Extruded, it can be transformed into seamless pipes of any thickness or length. From an unpromising start 50 years ago, the applications of polyethylene are limited only by the imagination. The remarkable properties of plastics in general is explained by the variety of structural possibilities of molecules called polymers. Polymers are extremely large molecules made up of thousands of repeating molecular units linked together in long chains. Now, these repeating units are formed from small molecules called monomers. In this program, we examine one of the simplest monomers, ethylene, and the process of converting it into polyethylene. Through a special type of reaction called addition polymerization, the ethylene monomer is first chemically reformed into the repeating unit for polyethylene. Because both contain the same number of atoms, their respective masses are identical. But the polyethylene molecule, containing thousands of repeating units, has a relative mass measured in thousands. It then becomes helpful to represent the reaction with this formula, where N represents the thousands of ethylene monomers required to produce the polyethylene molecule. The polymerization process begins with a gas containing ethylene monomers. A catalyst is introduced. The mixture is compressed to 1,500 atmospheres and heated to 250 degrees Celsius, creating tortuous conditions. The catalyst, benzoyl peroxide, is fragmented into short-lived free radicals. Bear with us. Because this formula is cumbersome on television, we'll convert the free radicals into a modified electron dot model. This radical contains an unpaired electron, scavenging for an electron to pair up with. Aha, target. The more loosely held pi electrons of ethylene. The result, a new free radical. Now, this new species with its unpaired electron in turn hunts down another electron to pair up with, finding it in the pi bond of yet another ethylene molecule. Contact. A larger new radical with a free electron. And so the polyethylene chain grows. And grows. But where does ethylene come from in the first place, if the molecule is not found freely in nature? One source is natural gas, which contains ethane, a good starting point for the synthesis of ethylene. So beginning from the ground up, we'll examine one high-pressure process for producing polyethylene. Natural gas first undergoes low-temperature fractionation. Ethane separates out at minus 88 degrees, and the remainder, primarily methane, is used in home heating. Some of this methane is bled off to fuel the conversion of ethane to polyethylene. The process involves heating the ethane in a thermal cracker, where the high temperature and pressure cracks or breaks down the ethane molecules to produce mainly ethylene molecules. The products enter the low-temperature fractionator and are separated into ethylene, hydrogen, methane, and carbon dioxide. The ethylene is further purified by scrubbing and drying until the product is 99.9% pure. Next, the compression stage, where there is some truth to letting industry do the rough, tough job. A mammoth compressor squeezes the ethylene to 1,600 atmospheres, after which it is cooled and sent to the heart of the system, the autoclave. It is no mean feat of engineering, because the high-pressure ethylene and catalyst are stirred mechanically inside the autoclave. What flows out is molten polyethylene in unreacted gas. In the separator, the unreacted gas is recycled back to the compressors, while the molten plastic is piped to a low-pressure hopper through an extruder, where it is cooled and cut into granules. The process we looked at, involving extremely high pressures, produces low-density polyethylene. Because these polyethylene chains are branched, the product is relatively flexible. There are, however, manufacturers who utilize lower pressures and different catalysts such as chromium oxide. This process is not as chemically violent, so the control reaction forms more uniform, linear molecules. These closely packed molecules, then, make a high-density, rigid polyethylene, suitable for structural materials. Whereas the flexible property of low-density polyethylene is ideal for such products as garbage bags and squeeze bottles. High or low density, polyethylene is sold to secondary manufacturers who meet today's demand and hope to profit on tomorrow's fad.